Welcome all to my ISIT 20 presentation. I'm Prathamesh. I'll be talking about limits on gradient compression for stochastic optimization. This is joint work with Himanshu Tyagi. Uh, so as the title suggests, we'll be looking at optimization problems where we have access to a first order oracle. Except in this case, the optimization algorithms don't get a direct access to the gradient estimates uh, supplied by the first order oracle. Instead, the algorithm has access to compressed versions of this gradient estimate. This particular model is of, along with being of theoretical interest, also has applications to the problem of distributed learning. So let me define this a bit more concretely. Uh, so we have a optimization algorithm pi, which we get to design, which queries a first order oracle O with the goal of minimizing an unknown function lying in some particular function class. The algorithm pi knows something about the function it's trying to minimize. For instance, it may know that the function unknown function f it's trying to minimize is convex, and it also has some idea about what the oracle output would be. So, for instance, it may know that the oracle output would be an unbiased estimate of the subgradient uh, at the point which it's querying. Uh, and this, so far, what I've described is the classic case of optimization with a first order oracle. Except in our setup, the gradient estimate supplied by the oracle passes through a Arbit quantizer, and only the output is available to the algorithm pi. Once again, we get to design this Arbit quantizer. In this particular paper, we restrict to a class of memoryless quantizers, which whose by memoryless I mean the output of the quantizer, the output distribution of the quantizer is only a function of the input gradient supplied by the oracle and nothing else. So this is essentially a refinement of the classical optimization with first order oracle framework. So, and here's why that is. Suppose we have, instead of r bits, we have infinite bits. Then the output of the quantizer would be similar to what you would get from the first order oracle directly. And it's as if the algorithm pi has a direct access to this first order oracle. And essentially, we can get the convergence guarantee um, which we would have in the classic case. What we want to understand in this study is, for a bunch of different families, what is the minimum precision R to which you can compress the gradient estimates coming from the first order oracle and still get the convergence rate when we would have infinite precision, or rather the classic case when the algorithm pi has can directly interact with this oracle. And we'll try to characterize this minimum R for a bunch of different problems. So let me define what I mean by this bunch of different problems. So in this paper, we look at LP optimization family, which is parameterized by this variable b lying in 1 to infinity. So it can be defined as follows. The domain X, which we'll be optimizing over, would be the LP ball of diameter d. And the functional oracle class uh, in which our unknown function f and the oracle with which our optimization algorithm interacts with can be defined as follows. The function f is known to be convex. The oracle O, upon a query X, returns an unbiased estimate of the subgradient of function f. Also, the output of the oracle is bounded in the Q norm, where Q is the Helder conjugate of P. So many of you would have seen this particular family, optimization family. Maybe instead of free here, you would have seen this particular constraint in expectation. So basically something like expectation of the Q norm square bounded by B square. So in the classic case, when there's no compression, these two constraints do not differ. Even if I have constraint in expectation, I would get the same convergence rate. Of course, when I'm compressing gradient, it's easier to look at the almost or case. But in the paper, we talk about how we can extend the quantizers we designed for this kind of a setup to the setup wherein we have the constraint and expectation. So, so for any particular family, a particular uh, performance measure to capture the difficulty in optimizing over that family is the following. It looks at the performance of the joint best optimizer, which is allowed P queries to the first order oracle, and the quantizer uh, and the best memoryless quantizer, which is allowed, which compresses the gradient to R bits, looks at the performance of this joint best pi and q for the worst case optimization accuracy over the class of functions and oracles satisfying all these three constraints. Um, and essentially, uh, if we were allowed infinite precision or, as I said, direct access to the oracle, it is known that we get convergence rate of order 1 by root t with some dependence on dimension, which changes with t. And our goal would be to attain this convergence rate of infinite precision at a minimum possible precision and try to understand what this minimum possible precision is for this different t. So it's essentially the minimum precision at which the composed oracle starts behaving like uh, the oracle when there's uh, when you have infinite precision, basically. So let's begin with characterizing this R star. So we'll start with the lower bound. Our first lower bound states that uh, when the variable p is between 1 to 2, I need at least d bits. I need a quantizer which at least allows a precision of d bits uh, to compress the gradient, and only then we can hope to attain the convergence of the classic case. And this is sort of reasonable to expect if we try to draw parallel to the vector quantization literature. Essentially, if you want your vector quantized output to resemble the input vector, you would at least expect that in any sort of reasonable metric you want the output to resemble the input, you would at least expect that you need 1 bit per dimension. So now for p greater than 2, however, our lower bound states that even if I have a quantizer which compresses the subgradients to d raised to 2 by p bits, that may be sufficient to attain the convergence of the classic case. So not d raised to 2 by p bit alone, but max of d raised to 2 by p and log d bit. Even with such a small precision relative to dimension d, we can get the convergence of the classic case. So the techniques for lower bounds are from Agarwal et al.'s Transit 12 paper, which derived lower bound for this particular family without any compression of gradient, and our ASAT paper, recent ASAT paper, which derived lower bound for optimization with compressed gradient in the Euclidean setup. So when p equals 2. And the basic idea behind coming up with lower bounds for this problem is to create difficult oracles for both optimization as well as compression. So in some cases will turn out to be lucky, and the oracle which is difficult for optimization is also difficult for compression. That's essentially the case here when p is in 1 to 2. However, for p greater than 2, these two oracles differ. The oracle which is difficult for optimization leads to the log d lower bound. However, it does not quite capture the difficulty in compression. For this purpose, we design another oracle which captures the difficulty in compression, not necessarily the most difficult oracle for optimization, but regardless of that, it gives us this d raised to 2 by p bound. So now we'll go about trying to achieve this lower bound. So before I describe our quantizers, we have this following convergence theorem for convergence with compressed gradient. So this theorem states that as long as we have an unbiased quantizer Q, there exists algorithm pi which differ for different p's to ensure that the worst case optimization accuracy over this class of functions and oracle for a given p, uh, the worst case optimization accuracy is as much as the convergence of, or rather the min-max accuracy at infinite precision into a blow factor of alpha by b, where alpha uh, is a parameter which is a function of this quantizer. So since our goal was to attain the convergence of classic case, all we need to do that now is to ensure that alpha is order b. So design quantizers which have alpha order b and will be done. So let me define now what this alpha is. So for p in 1 to 2, alpha is the square root of expectation of output of the LQ norm square. So look at the expectation of LQ norm square of the gradient of the quantizer output and take its square root. And look at the worst case of this quantity for all random variables which have the Q norm bounded by B. So this set captures all gradients which have their LQ norm bounded by B. And as I mentioned earlier, even if I have in the LP family optimization description, even if I have the almost sure constraint on the gradients replaced by an expected constraint which looks something like this, the convergence level won't change. And so I can just essentially replace the B there with alpha here and just bootstrap that theory to get this theorem. Now for P in 2 to infinity, instead of the only change in the definition of alpha here is that instead of Q here, I have the second norm. So this is crucial because if I had Q here, I would have had to bound, we'll end up bounding this quantity alphas later. I would have had to bound a much larger quantity, but now I have the much smaller second norm. The reason for this is that the optimal algorithm that is between 2 to infinity is the standard projected stochastic gradient descent. And that algorithm only needs the second norm of your gradient estimates to be bounded. So this turns out to be good enough for us. So essentially, this theorem gives us an idea about what we should do to design our quantizer. So basically, we want to design an unbiased quantizer Q because of this condition. We want our alpha to be order B to get the convergence of the classic case. And with the benefit of our lower bounds, we know that for P in 1 to 2, we want to design quantizers which satisfy both these conditions uh, while using a precision of only order D bits. And for P in 2 to infinity, a quantizer which satisfies both these conditions with precision of max of d raised to 2 by b by log d bits. So in the rest of the talk, we'll go about designing this quantizer. So we first start with quantizer design for P in 1 to 2. So notice in this case, we have an input y which, which has LQ norm bounded by b. And we want to make sure that the worst case expected LQ norm square of the quantizer output is small. So a trivial way of doing this is just to use a uniform quantizer which quantizes each coordinate between the dynamic range minus b to b with a high enough uh, precision. So basically log d bits for each coordinate roughly. So you use d log d bits in total and you can ensure unbiasedness, you can ensure alpha to be ordered. But we can do that will give us this gap of log d and we can cut down on this gap by doing something else. So and this trick is also handy for a bunch of different vector quantization problems. So what we do essentially is we take this input vector y, we split it into two different vectors. The first vector y1 collects all the coordinates which have their absolute value less than c, where c is less than what b was, and this ensures that y1 has a small infinity norm. So instead of now using a uniform quantizer between the range minus b to b, we use a uniform quantizer between the range minus c to c, and that so basically with a smaller precision we can get the same error performance. Similarly, for the second vector y2, since we collect all coordinates which have their absolute value greater than c, y2 must have sufficient amount of sparsity. And this is essentially because of this constraint. You cannot have with this constraint you cannot have all coordinates greater than p. P is being chosen appropriately for that reason. And then, although I have to bound the worst case L2 norm, I can bound the much larger worst case L2 norm and use a efficient quantizer for L2 since the L2 problem has been well studied. And that turns out to be good enough for us. And then we essentially combine quantizers for y1 and y2, and we have the following performance. The combined quantizer is unbiased. It has the overall alpha to be order B, and the precision it takes to do all of this is roughly a quantity less than d log d bits as well. And we remember our lower bound of d bits, so we match our lower bound to up to a very small multiplicative factor of something less than log d bits. So this sort of solves the question for p in 1 to 2. Now we'll move on to our achievability for p greater than 2. So once again we have input y which has the qth norm less than b. This implies that the L1 norm of this input y is less than b raised to d1 by p, and this essentially gives us our encoding algorithm, which is as follows. I'll just sample one of the coordinates of this input vector y with probability equaling the absolute value of that coordinate divided by this quantity b into d raised to 1 by p, and with the residual probability I sample 0. And this constraint ensures that this is indeed a probability distribution. Then I send that particular index to the decoder and the sign of yi. Decoder can use both these quantities and and this scaling factor to create an unbiased estimate of this input vector. And this simple algorithm is unbiased because of we scale it appropriately. It needs order log d bits because there are we just essentially the precision required here is to store the index. That's it. And alpha is b into d raised to 1 by p because of the scaling factor here. So straight away through this theorem, we can see that if we want alpha to be b, I mean alpha turns out to be order b when p equals infinity. But so and we match the lower bound for the case of p equal to infinity. But what do we do when p is lesser than infinity? Well, we just run different iterations of SimQ and take their averages. And this is our quantizer SimQ plus technically. So because I take average of k different iterations, the variance reduces in the output of SimQ, and we get a much better quantizer with a much smaller alpha in this. And the compression step used here is via the method of stripes. In other words, instead of storing k separate outputs of SimQ separately, I store the average by storing the frequency of each element uh, in 1 to d and 0, which is essentially the output of SimQ. And with this, once I store the frequency, I can recreate the average using that. And this sort of quantizer is unbiased once again, has alpha to be order b as soon as I set k to be d raised to 2 by p. So as soon as I use d raised to 2 by p repetition, and it uses a precision of k log d by k bits. That's the leading term here, instead of k log d bits. So by choosing k to be d raised to 2 by p, we get SimQ plus to be optimal for p equal to 2 and infinity. There's no multiplicative factor in these two cases. And in between 2 to infinity, there's a small multiplicative factor, but nevertheless, we are still very close to the lower bound. So summarizing, we looked at the LP optimization family, where we optimize instead of the standard gradients with compressed gradients. And we argued that d bits of communication were both necessary and sufficient in the case of p in 1 to 2. For p greater than 2, we could prove lower bounds and upper bounds which were much smaller than dimension of the problem. Yeah, so this concludes my talk. Thank you. If you have any questions, you can mail them. Bye.